exponential functions. This function is used for growth and decay. Growth like population growth, interest rates, decay like Halflife, that sort of thing. All right, so let's look at what an exponential function looks like, right? So this part, the left side here, is just the name of a function. This part's not important. You've seen this before. Remember, this is not f times x. This means f is the name of the function and x is the variable, all right, or the input. Here is the important part. This is the exponential function, right? A is a number. A is the base. It's not equal to 1 and positive. So we can't have -3. We can have +3. We can have 0.5 or 1/2 and 2, but we can't have 1, right? 1 to any power is 1, so it's kind of pointless. All right. Okay. So base is not equal to 1 and it's positive. The exponent is a variable expression. Right? I say variable expression and not just a variable because it could be anything like x over 2 or x over 50 or 3x. Right? We're not going to get too complicated with the variable expression, so it's most of the time just going to be x, but get the idea. All right. So some examples here. So if you didn't understand what I meant by the a, it's going to be a specific number. So a in this example is 5. A in this example is 1/2. Okay, and the exponent is x in both cases here. And here, pi. Remember, pi is a number. Don't be shocked or don't be distracted, confused. How do you tell somebody not to be confused? But anyway, pi is a number like any other number. It's just a really ugly number or something like that. Anyway, I'm babbling. So the variable expression here is 3x. The exponent is 3x. Here, the a is 3/2 and the exponent is x. All right. So let's look at some of those. All right. Yeah. This actually has a specific function. Right. This function has an economic application. Gosh, no, that makes sense. All right. So Jasmine's parents purchased a rare 1959 Gibson Les Paul guitar in 2010 for $12,000. Experts estimate that its value will increase by 14% per year. Jasmine's parents predicted that they will need about $60,000 by the time Jasmine is ready for college. What year will this guitar be worth $60,000? Okay, so we're going to apply regular interest for each year, right? So it's increasing, it's appreciating, appreciation, appreciating 14% per year. But in year 2010, it's worth $12,000. 2011, so we're going to increase the value by 14%, and this is what that looks like. So 12,000 is the original price or original value. We add 14% of that original value, so you do 0.14 times 12,000, right? 0.14 is the decimal version of 14%. Now there's a common factor of 12,000, so you take that out. So 12,000 divided by 12,000 is 1. And if you take 12,000 out of this expression, it leaves the 0.14. Okay? And so 1 plus 0.14 is 1.14. And that gives me 13,680. And for 2012, we basically do the same thing. So we take the value of 2011, multiply by 0.14, and add it. And that's what you get. Now, what I want you to notice is that pattern, right? So in 2011, it was 12,000 times 1.14. In 2012, it was 13,680 times 1.14. Okay, we'll get to that in a second. Now, so this 13,680, which came from calculating the 12,000 times 1.14, right? That's the same thing. So this 13,680 is the same thing, 12,000 times 1.14. So what we're going to do is factor this out. Okay, we're going to factor that out. Actually, all right. So when we factor that out, when we factor out the 12,000 times 1.14, right? It's in both places. We're taking that out. When we take 12,000 times 1.14 out of 12,000 times 1.14, it leaves a 1. And we take the 12,000 times 1.14 out of this expression, it leaves the 0.14. So what do we got? We got 12,000 times 1.14 times 1.14. So there's two of those. we write that in exponential form. We got this. Now that's the second year, right? This is the second year. All right, so we have a way to write a formula. So we don't have to sit there and figure out every one of them. Well, I guess we could. All right, but we have a regular formula. So the starting amount is 12,000. 1.14 or 0.14 is the increase every year. So we got to multiply by 1.14 though, okay? So that was after year 1, after year 2, after year 8, right? Because we have a formula, we don't have to figure out all the ones in between. After year 10, we're getting closer. Year 12, we get 57,000. Year 13, it's over 60,000. So now we have an answer. It's somewhere between 12 and 13. So the guitar is worth $60,000 after 12 years. That's year 2022. Don't forget, these are years beyond year 2010, right? From 2010. So once we got the value of 12, we just added to the original value of 2010, and we got the year 2022. All right. So we look for the pattern. We found the pattern, and then we wrote the formula. Now, so let's talk about growth and decay, or not. All right, currently the world population is doubling about every 61 years. To double, you multiply by 2. Okay, you don't add 2, you multiply by 2. According to UN estimates, the current world population is 7.7 billion people. So what we're going to do with this information, right? This is the 3 pieces of information we need to create a formula, to write a formula. And there it is. So we have the original amount of 7.7 billion times, and we want to double it, right? The population is doubling, so that's why the base is 2. And it says about every 61 years, so it's t over 61. Now, why is it t over 61? Well, for the exponent to be equal to 1, right, t would have to be 61. So 61 over 61 equals 1, so that'll be 2 to the first power. So you double, so that's the year it doubles, right? After 61 years, where t is representing the number of years, right, from the current year, I guess. All right, so 2, for it to be double, that has to be an exponent of 1. So 61 over 61. So you divide by 61 to keep it from reaching doubling until it hits here 61. All right. So that's it. And so that's how we write our formula. The original amount, and if it's doubling, we want the base to be 2, but we're going to divide the number of years by how many years it takes to double. All right. So that's the doubling formula. The base is always positive. Okay, now we're going to talk about the fact that it's growth. When the base is greater than 1, then it's growth, right? 2 is definitely greater than 1. If it's less than 1, it's going to be decay. But remember, it's positive, so we're not saying it can be negative 2. We're saying the base is somewhere between 0 and 1. Then it's decay. Let's look at another growth. Oh no, here we go. Growth, this is a typical interest rate for a bank, right? 24% interest compounded yearly. This is not like a savings account. This is a credit card account. So this is how much money you're owing the bank, okay? All right. So it's typically this formula, right? 1 is plus 1 plus 0.24. So that's the interest added, all right? Population doubling every 10 years. So here, A is the original amount, 2 is the base. If it's doubling every 10 years, it's t over 10. Decay. Half-life of carbon-14 is 5,370 years. So A will be the beginning amount of carbon you have. 0.5 is the same as half. T divided by 5370. That's our half-life formula. Okay, let's do an example of where it's depreciating. The value of a truck bought new for $28,000 decreases 9.5% each year. Write an exponential function and graph the function. Predict when the value will fall below $5,000. Okay, so here. So this is our depreciation formula. The original amount is $28,000. It's decreasing 9.5%. So it's 1 minus the decimal version of 9.5%. That turns out to be then 1 minus that is 0.905. Now this is our formula. Let's graph this. So there is the graph, right? At t equals 0, anything to the 0 power is 1, so it's 28,000 times 1. So there's our y-intercept, right? That's where t equals 0. T equals 0, plug it in, and you get 28,000. Now, after 5 years, it's about here, and then 10, and then 15, and then here. This line is the line y equals 5,000. They intersect at 17.259. So that means it's about year 17, a little bit after year 17, or during the 17th year, this truck will be worth $5,000 or less. All right, the value of the truck will fall below $5,000 in the 17th year, right? So after the first quarter. All right, okay, so that was the formula. Initial amount times whatever the rate is to the t power, to some power, and t here is representing years. All right, okay, so this is a summary of the exponential function. Alright, so here we have a general growth or decay. A is the starting amount, the percent rate in decimal form, or the minus percent rate in decimal form. Okay, it's positive, you're adding if it's growth, you're subtracting if it's decay. Half-life or doubling, right? So half-life looks like this, with the starting amount A. Half-life, N is the time it takes for half of it to decay. So that's what this N is, right? However long it takes to decay, half of it, that's N. So if it takes 20 years, if an object has a half-life of 20 years, then N is 20. Here, same thing. This is growth. This is doubling. So the initial amount is A, and M is the time it takes for it to double. So you divide by however many years it takes to double. We did the world population where it doubles after 61 years, so M was 61. What's expected from you on this topic? Identify an exponential function, right? And determine whether or not it's growth or decay. So remember, if the base is less than 1, then it's decay. If it's greater than 1, then it's growth. Write an exponential function from given information, right? Given the initial amount, that was that capital A in the front, given the rate of growth or decay, so you got to do 1 plus the decimal version. If it's growth, 1 minus the decimal version of the rate if it's decay. And given the time it takes to double over its half-life. Okay, so these are two separate types of givens, right? In this given here, they're talking about something doubling or having its half-life. So you would do it a little bit different. Okay, so if it's double, it's A, the initial amount, times 2 to whatever power, and it's T over however many years it takes to double. Or if it's half-life, it's the initial amount times 1/2 raised to whatever its half-life is, T divided by whatever its half-life is. Okay, and you're going to use that function to predict future values. Okay, sorry, it's 6 a.m. and I'm doing a lousy job. But that's it. I'm done. Have a good day.